So, in the first segment of today's agenda, we're going to be talking about lookalikes on the network. And I'm going to start with you, Rob. Why is it that things aren't always what they seem when you're scanning the network?
Nefarious deeds. So everybody's first going to immediately jump to honeypots, of course, and that is definitely a thing. But there's also, arguably even more common, are things like simulators, probes. In the OT space, we especially see a lot of HMI devices that if you're just doing passive discovery, it's actually difficult in some situations and some protocols in OT environments. Passive discovery can't always differentiate between which end is which in a reliable manner. So sometimes you'll get HMI devices being identified as PLCs or whatever, and I'm gesticulating here, but my hands are up here, and so you'll get HMI devices identified as PLCs or vice versa. Like the FINS protocol, it's actually really difficult to tell which direction it's going unless you initiate the conversation. So active probing really comes in handy there, which is something we do, which is awesome. And then simulators are also extremely common. Probes are extremely common. Uh, I have a large set of simulators, OT simulators in my house that I use for testing or whatever. And when you probe the network, when you look at passive network traffic, when you do active probing of the network, they will show up as whatever they are, devices, and you can set them to be by default. You can say, oh, report yourself as a simulator or whatever. But if you want to get uh, most of them, if not all of them, let you say, no, pretend to be this specific kind of device or whatever, and then suddenly they'll look like that device unless you know what to look for. There's also rogue devices, which it sounds scarier than it is. I mean, every now and again, yes, you might have something that was put there with nefarious intent, but there's also just devices you forgot about, or the whole shadow IT problem of somebody set something up because they needed it and they put it on the network and now it's there, and they know about it but you don't. And then compatible devices, which are just devices that aren't necessarily from the same vendor that they are speaking the protocol for, but they say that they are. They do that just for the sake of interoperability. Um, so yeah, so there's lots of good reasons, and then also honeypots.
So, Rob, how good are they at being a lookalike? Because, we've all, I'm imagining with this audience, all of us have faked a user agent in an HTTP client at some point, right? Like we've all
Mhm.
done this. Like, but how good are these devices or these lookalikes at pretending to be something else?
Um, it like anything, it varies. Some are particularly good, um, and actually, I think there's. Can you jump to the next slide, please? Sorry. Yay! Uh, Behold my incredible slide making skills. So the a lot of times they're almost indistinguishable, right? But there's very often a few things that you can catch that are little giveaways. Um, so one of the most common is, for example, TCP, IP stack stuff, which Tom did an amazing talk during the last runZero hour. I highly recommend you go back and watch the recording. It was really, really cool about identifying TCP IP stacks just by looking at the network traffic, one ping only kind of thing, to quote the Hunt for Rod October. And so it's if you see something that's saying, oh, I'm a this kind of embedded device, but then the IP stack is pretty definitively Windows or something, you can be like, oh, maybe it's not. And TLS fingerprinting, again, something we've talked about extensively on the runZero hour. You should probably check that out too. It's really cool. But even some more subtle things that are interesting, like a lot of in the OT space, a lot of these devices aren't super particularly powerful devices, and more importantly, also prioritize other traffic over some of these probes. And so just even things like response time, if you connect to this device and it is, it's immediately responding back, you can be like, this is a little strange. It's either very unloaded or it's, running on faster hardware with a different priority. And there's also one, what's it called? Gas pot for ATG that I remember we it uses different line endings than the authentic hardware. So for those of you who are fascinated by line ending things, so you can have the common line endings are OD and OA, character turn line feed, and some systems just do line feed. Some systems do character turn line feed. And the authentic hardware does, I think it's character turn line feed, but then the honeypot only does line feed, and so it's interesting to see the difference between there. There's just some subtle differences that kind of stand out, which is really interesting.
You know, to my mind, the line endings ones is most interesting because, you know, when you're programming anything to do with files and you're trying to make
Mm-hmm.
it portable between Linux and Windows, right? You always run into the issue, like the first time you do this, at least, you always run into the issue where like the line endings are different, and then like you have to adjust your code to accommodate that. And
Mm-hmm.
so it's always been an annoyance that it's CRLF or LF. But I
Mm-hmm.
find it super interesting that for fingerprinting purposes, it's actually really,
Mm-hmm.
really useful to see what those line endings are, because it's like a tell
Mm-hmm. Oh
for.
yeah, there's lots of little tells, and I'm a horrible poker player, but I'm great at fingerprinting, which is, I guess, an adjacent skill. And like there's other little quirks too. Like there was one, I can't remember which specific device, but the format of a date header was slightly different in the authentic device versus not, and things like it was pretty cool. That was a fun thing to find. So.
Tom, do you want to weigh in on the lookalikes on the network?
Oh yeah, those are always fun to find. And there's certain legitimate use cases of those, as you mentioned, and then certain other ones that are just accidents. The things that spring to mind for me are, and I forget the vendor. There's an IoT device that basically you install on Windows, but then uh, the the IoT stack that gets installed on top of it takes over the TCP stack, where they run side by side. And it was either Profinet or one of its adjacent type technologies, where it's basically Windows and then the stack on top of it, but it can look like either one of them depending on what you're talking to. There are things like Checkpoint, where Checkpoint has its own operating system, but it has a custom TCP stack. Um, so the stack behaves differently than the operating system otherwise would. And then there was one that HD mentioned something the other day that reminded me that, if I recall correctly, there was a C2, I think it was a Cobalt Strike C2, where one of the headers, the line ending thing it was just off, or it was very particular where it was behaved one way except for one particular line. I forget exactly what the details were, but it was an implementation detail that once you saw it, you could check for a particular field. And if it ended a certain way or behaved a certain way, like, oh yeah, that's Cobalt Strike C2 or something like that. So it's always neat to find, and sometimes it's easy to overlook unless you're like really down in the weeds going, okay, I have a bunch of things that look like the same. I'm gonna like side by side diff them and can make sure, like, does every little thing look exactly right? And sometimes it's not just different products, but different versions. They incorrectly implemented line endings, and then in some version they fix that, and now you can say, okay, before this it's this product, and after this it's this version of the product.
That is hilarious. Um, so we'll probably end the segment here with a final question to HD. How good are we, runZero, at identifying the real thing from the lookalikes on the network, would you say?
We've got a different take. So a lot of security tools, they really try to say, well, we want to find fake stuff and tell you it's fake. We don't care. We'll tell you what it acts like. And if you want to put a honeypot on your network that looks like an OT device, that's great. We'll identify it as best as we can. But we may end up identifying different parts of the device differently because of the quirks. So for example, we could show that the OS is really Windows, but the hardware is actually this OT device because it literally is running on Windows, but it's a fake emulator on top of it. So we try to show you as much about each individual service and layer as we can, even if the device itself is basically fraudulent. Another really fun technique I like to do is look at the ping response times for ICMP versus ping response times for TCP SYN request. For a lot of IoT equipment, the TCP path is much slower than the ICMP path. So you have like an APC network UPS on your network, for example, do a just normal ping command against it. Then use hping to do a send request. You'll see the send request takes about 3 times as long to get a reply. Now, if you're assessing a device and you want to see, is this actually an OT device or not, ping it, then do a hping. And if the RTTs are the same, it's probably running out of PC.
That's amazing that we were able to leverage that kind of detail to sort of differentiate the real thing from the lookalike. All right, so that is it for this segment. We're going to move on to the next segment here, which is about fuzzing. And Tom, I'll start with you with a question. So when you're developing a scanner or when you're scanning the network, how much can you trust the data that you get back?
Oh, for what we do, you can't. You have to assume there's any number of things that have gone wrong or intentionally or accidentally with the data that you're collecting and processing, and pretty much code defensively. And that's, you know, that's pretty much what the sort of the goal here with this particular topic is, to sort of help put in place some controls to protect against that, but also do it in a scalable way that is efficient and effective, and sort of in a certain degree emulates that those various sources of untrustworthy data.
Okay. So, for many of us, we're familiar with like fuzzing of URLs, fuzzing of passwords. So what do we mean here by fuzzing when it comes to fingerprinting?
So fuzzing in general is basically a process through which you take either a set of random data or a set of valid but mutated data and pass it into some logic with the intent to try to discover or trigger some sort of bug that you don't otherwise know about. You know that it behaves correctly when you give it good code, but you want to throw unknown values at it, unexpected values at it, and make sure it handles those correctly for cases that you just didn't even think about. Go ahead and bop over to the next slide for me, please. So our challenge, sort of as you mentioned, is that like in our active and passive data collection, we deal with a ton of untrusted data. Matter of fact, on the scanning side, on the data collection side of it, more often than not, it's untrusted data. We rarely get data which we actually want to treat as trusted. Those incredibly few and far between, and we have to make sure that that whenever we handle this data, whether it's unexpected because of its protocol difference, or it's corrupted, or it's been hostilely constructed, that we've coded defensively enough that it doesn't cause any security issues, that doesn't cause our product to fail, or it doesn't inject just garbage data into our results. All of those are undesirable. And when I say hostilely constructed data, like, there are a variety of researchers and professional bad guys out there that like to craft payloads, either actively sent or broadcast out on the wire or whatever else, with the intent to cause various programs to process them and either cause a denial of service, execute code, whatever else. And we want to make sure we handle that. Somebody has intentionally crafted something that gets past your normal filters, but then misbehaves at a particular part in your logic. And we want to be able to be so robust that it just bounces off of us with no negative consequences. All right. And next slide, please. So the approach that we have taken for this is that we're doing a couple things here. And just for context, we use Go internally. Most of us, I think all of us, love Go. It has a lot of features that are fantastic. One of those that I really like about it is testing. Testing is a first class feature. It's built into the language. It's not an add-on that is an afterthought. It's not a third-party package. It's there, and it does an amazing job. And because it's a first-class feature of the language, it just works in pretty much every case you would want it to work. It works great with CI. It works great across the board. But what we do is, particularly for our probes and our data collection logic, is we make sure we try to have as robust a test as possible. We try to take, for example, valid examples of packets that we may be processing and run those through the test. And then where we know we've had bugs in the past, we anticipate bugs, we run that data through. And the goal there is just to try to make sure that our logic is as solid as possible. We pair that with verified coverage. So one of the things that Go can do is that you could have it emit a report that shows the coverage of your tests. So you literally get a color coded output that indicates like, here's your logic, here's your code, and then here are all the portions that the tests have exercised, and here are the portions that it hasn't. And you can use that to improve your tests. You make sure that you have solid, robust tests. And that just improves quality overall. And then the last thing, the thing that really we want to talk about today is fuzzing. So we've adapted fuzzing as a set of techniques to improve the quality of both our internal code and third-party packages that we use. Like everybody else who has a Go-based platform, we use third-party packages to help us out with various parts of the logic. And we want to make sure that those are as robust as well. People make mistakes. People are human. There are weird errors that say static analyzers can't catch or linters can't catch. And we want to make sure that we're catching it both in our own stuff and in third-party packages. And fortunately, just like tests, fuzzing is a first-class feature in Go. It is basically a specialized version of Go tests. So instead of like a normal test where you give it very distinct inputs and then you expect specific outputs or validated outputs, what the fuzzing does is it dynamically injects data in the place of those static inputs, and then allows you to do validation on the other side. Yes, it allows you to do validation on the other side to make sure that you're getting what you expect and it doesn't cause things like panics and all that. And well, I jumped a little ahead and I covered fuzzing there. The remaining topic here is guided coverage. The great thing about Go, both testing and fuzzing, is that whenever you provide Go fuzzing with really good input corpus, like for example, the test that you already have, you can feed that into the fuzzer, and now the fuzzer has a place to start. So instead of just injecting random data into your logic, it can take your test and know, okay, this is data, this is input that is known to exercise different parts of the code. And then it can mutate that in various places and observe the results and see where the new inputs are exercising your logic differently, and use that to guide where it's doing the mutation. So we can say, okay, I've mutated these things over here. They didn't make a difference to the cover. We didn't touch new code, but these bits and bytes over here, they did. So we're going to keep permutating those and see if we can't get further down into the logic and get better coverage, get more of that logic abused to try to find those additional errors. And by having really solid tests to feed into your fuzzer, as well as using the guided coverage, you get much better outcomes. You can go from things that take days to fuzz to find a bug to literally finding bugs almost the instant it finishes setup.
All right. So I think on the next slide, you have some results to share from what we've done here.
Yeah. So the results were, depending how you look at it, both good and bad. Like they were, the fuzzing process was very productive, and it found a lot of things that needed to be addressed. So all in all, in like our first major push through fuzzing, we found over 100 panics or other bugs that we found and fixed. That was both in our own code and in third-party code. They range through a variety of failure modes, and I'm going to get into those in just a second to sort of talk about sort of the different ways things fail and root causes and things. But it was quite a gamut of issues. And in one particular case, we had one upstream package in which we found 80 of these. Fortunately, the worst impacts for that particular package were sort of put behind some guardrails that basically said, if you see a panic in a particular subset of the logic, don't actually panic, just return nothing or return an error. And so in any of these situations, whenever you get bad data that comes in, you just get no result. So in our case, like if we were processing packets and processing the data from it, we might get nothing from the packet as opposed to having a panic or some other undesirable outcome result. And then we've contributed fixes to 4 different upstream packages. In a case or two, there was a single, like we found a panic or we found some other misbehavior. In a couple cases, there were nearly 10 apiece of both panics and logic bugs. And therefore, they happen for a variety of reasons. I'll cover a little bit more, but I don't want that to sound like it's a negative thing for that package to have not already discussed them. Some of them were hard to find. They were, once we had the fuzzer to find them, reproduce them, tracing to the card was difficult. I mean, the code is complex. They're processing complex packets. So like anybody can make the mistakes that cause this. And in some, like a couple cases, they were due to variations in the protocols or the data that aren't common. Like they implemented 95% of a particular file format or data format or whatever else, but you got these corner cases over here that are not common. And so like they might not have implemented them as well. And like anybody can make those decisions, it may make those bugs. Everything in programming is a trade-off.
And something I just want to point out real fast for those of you who aren't familiar with Go, panic is kind of it's explicitly not an exception handling thing. It's a you've reached a point of software, you've reached an error that is not recoverable, quote unquote, and you can go back to and recover and all that. It's essentially a kind of like an exception throw, but subtly different. But it's important to know that Go it doesn't violate memory safety. There's nothing like that. Like a panic is still safe, as it were. It just sounds scary.
What's interesting about some of these bugs is they affect libraries that are designed to parse packets passively off the wire. And so if you're running any kind of solution that's security related, like looking for an NDR, looking for attacks, looking for things like that, and someone's able to trigger one of these panics, it'll actually cause that packet to not get processed, which could cause the entire stream not to get processed, which means you don't see the attack afterwards. So there's some neat anti-IDS impacts of these bugs.
Yep. There was the old when you have overlapping packets and TCP streams with different sequence numbers, and the IPS will see one, and the EDR will see another, or the endpoint will see another, and yeah. Protocols are fun.
Yeah, that's a great example of the old concepts of insertion and evasion, where you can insert packets that, as you said, the IPS doesn't process, but the target endpoint does. So yeah, those are great examples.
So before we get into the common issues, a question for Rob. When you're familiar with our code base, when you saw these numbers,
am I? No, I'm kidding. Sorry.
When you saw these numbers from Tom's analysis, were you surprised or?
Not surprised would be a strong word. I was. I am always in awe of Tom's abilities, and so when he was like, "Hey, Rob, I found this number of vulnerabilities," I'm like, "Of course you did. This is great." So, but no, and in any large code base, third party, whatever, there's going to be some stuff that's going to get teased out, and the best part is when fuzzing finds a panic or finds something, but the panic is handled already. You've got guardrails, like Tom was saying. That's always fun and nice to see. But no, I was not really surprised. I was just pleased and amazed with the speed, the alacrity with which they were discovered.
Yeah, from my time doing assessments, we always said that when you come back with a lot of issues, that's bad. When you come back with no issues, that's even worse.
Mm-hmm.
Yeah.
Mm-hmm.
So, all right. So, Tom, let's dig into some of the common issues that we found.
All right. So there's a couple classes of issues that we found, and the first one is panics, as Rob is talking about there. Basically, your code is misbehaved in a way that the Go runtime has decided is dangerous. It's going to end the program execution or end a particular section of logic, depending on if you have handlers in place. It's sort of like exception handling. As he pointed out, it doesn't result in sort of like memory safety issues because Go is a more memory safe language than a lot of your other common mainstream languages. But panics they're across the board undesirable. It means something went wrong that we probably should have handled better. And so when we look at the panics, we can kind of group them into a couple a couple of different mechanisms that trigger them. So as I mentioned, we're processing untrustworthy data, and we often get like a blob of data that either comes off the wire or is in response to a scan. And we've got to process this. We tend to already have a sense for what type of data this is. And so when we're processing it, we apply a certain level of logic to it. And it may, for example, try to iterate over that data, pulling out fields such as the length of the next piece of information that we want, the type of the information that we want. It really depends on the protocol that we're speaking, that we're talking about. And so, for example, if you're reading a piece of data and you think that like the next 2 bytes are the length of the following piece of data that you want to collect, you pull those 2 bytes out and you say, okay, my length is this, and then I'm going to go grab that much data from my blob. And if you don't check to see that your actual data is that long, like if your length says that that your next field is 512 bytes, but you only have 10, then in Go, when you try to index into your total blob of data out to 512, or in this case, it's 2 bytes, 514, then you're going to trigger panic. You can have an invalid index, and that'll cause your code to panic. And typically, there's some relatively reasonable ways that you can check for that. When you read the length, check is the length that the field claims bigger than your data. And if it's bigger than your data, then you just, all right, we got an error. And then you handle that in whatever is appropriate, whatever mechanism is appropriate. This can be made a little bit worse when you have loops. So if you have a block of data and you're just iterating over the block of data and you read the length and the type and the value, the first ones may have been fine, but you get towards the end of those, you may have miscalculated as to how you check your links. You may have, like, for example, said, is my link equal to or less than the data? And what you really should have said was just less than the data. You can do you make an off by 1 error and just iterate past the end of your data. You get an invalid index, your program panics. And those are type of things where if you have tests, you could be testing the happy path, but you forgot to test when the size is just incorrect, and you can result in a panic. Another one that became like a whole thing that is really interesting and probably overlooked by quite a few folks is if your program that you're building runs on 64-bit platforms and 32-bit platforms, you can run into issues, particularly in Go, where the size of certain types changes. So on 64-bit platforms, Go's integer type is 9 quintillion plus or minus. So N64 is -9 quintillion all the way up to +9 quintillion and some change. So int equals int64 on 64-bit. But if you move to a 32-bit program, the size changes to something significantly smaller. It goes from -2 billion to +2 billion. That's significantly different than 9 quintillion. And if you're specifically typing your data so that it's int16, int32, int64, those stay static. You know what you're dealing with. You know what you have to play with range-wise, whether it's uint or int. Like, what sizes you have. But int's a special case where it changes on the platform, and so it may behave in ways you don't expect. So on a 64-bit platform, you run your test, everything's happy. You run your fuzzers, discovers no problems whatsoever, because your checks there are perfectly sound. They work. For example, if you're checking to see if that size you read is bigger than the total data size, and so, for example, the claim size is 4 billion and you check your total data size and it's 10, well, cool. You determine that your length value is invalid and you can handle that error. But when you go to the 32-bit platform, you may read the 4 billion value for length, but whenever it shoves it into an int32, it's no longer 4 billion. It is now -2 billion and some change, depending on where it lines up. So if you're doing that length check again, you go, well, is -2 billion smaller than my data size of 10? Yeah, it's significantly smaller. So it gets through the check, and then now you're operating on some wildly invalid value. You're either trying to index by -2 billion or somewhere on that sliding scale below 0, or you allow some other logic to be enacted on that data size, on the remaining data that's also invalid. So that platform bug is an interesting one. that some people will never have to worry about because they're purely 64-bit platforms, and other people will be like, oh crap, I didn't think about that. Like it's not something that necessarily shows up, particularly if you're not doing fuzzing.
So basically, all models break when you change parameters and bounds, right? That's
Okay.
the way it is. Tom, so we're gonna need to skip over to the recommendations section for this segment. But to the audience, if you are interested in Tom writing a full blog post on everything in here about fuzzing, please in the Q&A channel, Q&A box right now, just type yes. Type yes if you want Tom to write a blog post on all of these details that he's discovered from fuzzing. But for now, we'll just talk about the recommendations, Tom.
As a panelist, can I type yes? How do I type yes? I need to type yes.
You can type. We'll assume it's yes. Hey, Tom.
Yeah, sorry, folks. I get a little excited about this. I love this topic. So recommendations, guardrails on values from untrusted data. If you're processing untrusted data, if it's something like a type length value type of field where you're getting links, like check to see if the link that claims will actually fit in the remaining value, the data that you have. If you're expecting to get a value like a string or a field type, validate that that's even legit. Is it one of the recognized types that are codified in this particular protocol? Is the length of the string something that is even reasonable? Like zero length key for key values, probably not legit. 10,000 character keys, also probably not legit. Like put some reasonable bounds on that. There are certain functions that are more safe than others. So for example, you can make a call to binary big Indian uint16 that expects 2 bytes, but if you only give it 1 byte, it panics. Well, instead of doing that, use something like binary read that will read into a particular variable of a certain size. And if it isn't given enough data, it generates an error safely. And if you check that error, which is also critically important, then you can process the data. If it's too short, if it's wrong, if there's something wrong with it, you can handle the error as expected, and everything remains in your control. You don't have panics, you don't have invalid data. The third one is test. Solid, robust tests. Test. Go makes it relatively straightforward. Leverage that. It will help you all the time. And if you're super concerned about performance, benchmarking's first-class citizen built off the testing infrastructure. So like do that as well. I talked about test coverage. Check your test coverage. It's built into the language. You can run a command that'll tell you what your coverage is, and you can use that to improve your outcomes there. And then, as we were talking about here, implement fuzzing. And when I say that, I don't mean just like implement fuzzing, let it run until it panics. Do other things. Check the duration of your test. If your particular piece of logic should complete in like a quarter of a second, but it takes 10 seconds to run, you got a problem. You got some kind of loop, you got some kind of resource constraint issue. So check the duration, like start a timer before, process the data, check the time. The result size, if you're expecting to process some kind of data and extract, say, a map of 10 entries and you get 1,000, that's invalid. Put some guardrails in there. Speaking of validation, if you're expecting to get some kind of result out, then that logic should either return an error or return a valid result. So you can check to see if you got no error, and then run your validation through the output and see if it's sane for the context of the particular data that you're working with. And so that gives you the ability to say, not only am I checking for panics in my code, but I can also check for other negative outcomes that may happen through throwing garbage through a particular piece of logic. And the final thing there is something that we didn't really get into, but on the guided coverage, there's no guided coverage for 32-bit. So if you're going to be testing on 32-bit platforms, using like Go Arch 386 on a Linux box, just know it's going to take longer. It's going to not find as many issues simply because it can't see how it's moving through the code and what the coverage is. And so you just have to be a little more patient with it or give it more time to find the issues. But it is definitely useful to do that. Even if your targets are only 64-bit, it will still find logic bugs that you made on the 64-bit side with your guardrails. You're like, oh, my guardrails, we probably will never run into this, but they were insufficient. And so I still need to fix them. And I think that's it.
And a couple, so one note that is interesting about Go is that when you have a 32-bit build of Go, your native int becomes 32 bits. A lot of folks just don't plan for that. They assume that int is all 64-bit regardless of OS, and that change for int becoming 32-bit is actually a really big deal across a ton of code bases. Lastly, I've got an anti-recommendation. Like, don't just put all of your parsing code into a panic handler and blindly say, okay, that was great at panic, whatever. Like, that doesn't work. There's a bunch of reasons why it's a really bad idea. It's, terrible code and you're evil if you do it, but it's also can lead to cases where you can leak memory, you can cause, CPU utilization. Like, there's lots of other side effects of fuzzing besides throwing a panic and go that are worth avoiding.
Yep. Sometimes those can also hide other bugs. Like, for example, if a protocol changed on you, there's a new version of it, or a rarely implemented aspect or feature of a particular protocol that you're not handling correctly. If you hide the panic, you don't know you're handling it correctly. But if you do something reasonable about that particular failure mode, it might make you aware of something that you can improve your code with. It's not just a bug. It's just like, now I can address this additional version of a protocol or attribute or whatever else. We see vendor custom extensions all over the place on things that should be very strictly defined by RFC. RFCs are barely recommendations.
Yeah, they're recommendations. The requests for comment.
Thank you, Tom. So, folks, I'm sorry we don't have enough time to go into more details about what Tom has done with fuzzing. But again, put yes in the Q&A box right now if you want Tom to write a blog post on this, and you can go into all the details that we didn't have time for today. I'd love to see more yeses in that Q&A box. All right, and we'll move on to the third segment for today, which is the rapid response roundup. So these are all the vulnerabilities that we covered in the last month. So for those of you who are not aware, this team that you're looking at right now is the one that goes out and researches what are all those proxy indicators that allows you to identify devices that are potentially vulnerable to a CVE based on asset details alone. And the great thing about this is you can go and identify very quickly what are all those devices that you need to go to remediate without having to rescan your network. Without having to wait for a vuln check, without having to run a full vuln scan, you can actually use runZero without having to rescan the network to go find those devices that are potentially vulnerable. All right. So let's start with the first one that we covered in the last month. Rob, I think this one's yours. ConnectWise.
ConnectWise, yeah, and rapid response roundup. That's I'm not gonna be able to say that 5 times fast. So yeah, ConnectWise is it's a hosted screen sharing service, remote control kind of thing, and yeah, this was This was an authentication bypass issue, and it was fun. It was interesting. You can see in the query here that the product used to be called. It was originally Screen Connect. Then it was renamed to Control for a couple of years, and then it was renamed back to Screen Connect. And so we do actually have you can even tell what version is going on, but you can find you can find it via both names, hence the and the or in our query, which was kind of fun to play with. But yeah, definitely an interesting issue because it was just complete control, hence the CVSS of 10.
All right, and let's go to Microsoft Exchange. So that one's you, Tom.
Yeah, so there was a vulnerability in Microsoft Exchange that is due to the ability to take NTLM hashes, which is OG pseudo encrypted values for passwords, and pass them around. So you can, it's back up a little bit. There's a type of attack called pass the hash, wherein when you want to authenticate to a target, you don't have to give it a username and password. You can just give it the hash. Thanks, Microsoft. So we've seen this fixed in a variety of products over the years. Exchange has this particular vulnerability where if you can capture the hash from someplace, you can hand it directly to the Exchange server and become authenticated as the user without having to crack their password. You don't have to use all this time-consuming effort. You just hand it straight to the Exchange server, and it authenticates as the particular person you've captured the hash from. A thing of particular interest is that in February of this year, there was a vulnerability in Microsoft Outlook in which you could send a victim a particularly crafted email that had some calendar-related headers, and those headers would cause their client, without any action from them, to authenticate to your target of choice, handing you a hash. So you could then send a person an email, get the hash, take the hash, send it to Exchange, and authenticate as that individual. That's not the first time that's happened. It's happened several times over the various years. I think there was at least one last year. So I think that's of a particular concern there is like, yes, we have this problem. with Exchange, but also we know where to get the hashes because there have been vulnerabilities that are in the ecosystem within just over the last month. So that's why I think that one's particularly of concern. And if you get them from admins, you could have the keys to the kingdom. Like once you get into Exchange, you can often leverage the domain admin, but you can often get into mailboxes, which is usually a lot more interesting.
All right, thank you, Tom. So I'm going to skip over OpenEdge for a moment. We might come back to it, but I want to go to Team City. So HD, Team City. This is like it's like every other month. It feels like in the last 6 months we've seen something from Team City.
Yeah, for all these bugs, it's very much like where there's smoke, there's fire. You see one kind of in the wild exploited vulnerability, and then you see a few more every month afterwards for a while until the code base gets shaken out enough. In this case, there was a Team CD authentication bypass vulnerability back in February that was already exploited in the wild and pretty gnarly. You could just basically bypass auth and use the bypass authentication to run code. Rapid7 team found a similar but different bug, as well as a directory traversal. Published or contacted Team City, reported, or JetBrains reported it. JetBrains then kind of didn't follow the disclosure schedule, shipped the patch early, which caused Rapid7 to push the exploit early. And now JetBrains is currently blaming Rapid7 for the exploitation, even though these vulnerabilities look like they're straight out of 1995. The authentication bypass is one of those like question mark JSP equals something dot JSP semicolon. And the directory traversal is literally like /res/ dot dot dot. Like that's all there is to bypass these. So on one hand, there's a spat going on between the vendor that found it and JetBrains. On the other hand, these vulnerabilities are absolutely trivial, and it's surprising that they weren't found the first go around in February.
Yeah, and I think, I saw some other conversations around this. I mean, it really goes to show the importance of having POCs when you're publishing these vulnerabilities. Is that right?
Yeah, a lot of folks say like, well, what's the point of publishing an exploit in the same day as a patch? Well, the reason is as soon as the patch is out there, everybody who has an incentive to exploit it, aka the bad people, are already working on reversing the patch, finding out how to exploit it, and it's really everyone else that's behind the curve. All of your lovely security vendors, whether it's your AV, your EDR, or even folks like us, we depend on information being available about the vulnerabilities to be able to help our customers protect against it. Without that, we'd have to go do the full work reversing the patch as well. So as soon as a patch is released, not when the details are released, that's when the clock starts ticking for exploitation by attackers. Over the last year or so, I've seen quite a few cases where a vulnerability that was patched but had no public proof of concept or other details was being exploited in the wild shortly after, and that had everyone else scrambling, trying to figure out like, okay, I didn't realize I had to care about the one. I didn't realize it was exploitable. Like the proof of concepts and exploits really help everyone understand what the impact is and really put a spotlight on the vulnerability so that all of the, everyone from the people running the software to the security vendors who help their customers protect against these attacks can get ahead of it.
Tom, did you have a comment on that one?
I did. I also think that in addition to that, it is critical for certain classes of vulnerabilities to have the ability to validate that your corrective efforts have been effective. Sometimes a vendor issues a patch and it is insufficient to fix the problem. They may have misunderstood the problem from the people who initially reported them and they fixed the thing, but it wasn't the thing. And so that's important. Also, there are many cases where you have a particular risk that is either mitigated through a patch or reconfiguration. So you have other mitigation options until such times you can apply the patch. And so having the exploit available to you in a usable form allows you to say, okay, I can't patch right now, but I can turn this feature off, or I can implement a filter. I can do something else as a mitigating control. And then you can use the exploit to validate that your mitigation was sufficient. And you don't have those options if you don't have an exploit. If you can't reproduce the attacker's behavior, then you can't reasonably check to make sure that your mitigating controls are sufficient.
Yeah, you just nailed it on the head. If you can't reproduce the problem, there's no way to verify that the fix actually fixed anything. So yeah, +1, multiple +1s to what both of you just said. All right, let's go on to Apple, Tom. Apple. This turned out to be many apples, is what it seems
Yeah,
like.
it did. Yeah, so Apple released some updates initially for iOS and iPadOS. They have since been expanded to macOS and the rest of their ecosystem there. And originally, they basically for the most recent version of iOS, 17.4, it had like 4 CVEs listed and said, "Hey, we're going to come back later with some more." But 2 of those are particular interest because they noted that the exploitation in the wild had been identified, and these particular vulns they required you to already have access. You know, if you can already do arbitrary memory reads and writes, then you can bypass the memory controls. So those are things like if you're already on the device, you can now do more nasty things, and probably escapes. And there's probably more interesting to nation states than say pen testers and whatnot. They came back a couple days later, and it went from 4 CVEs to 40. So the whole there's a whole swath of things that were they to be leveraged in conjunction with each other. You know, for example, you can view an image, view an HTML file to execute code. Well, now you can execute code, then you can chain some of these together to potentially gain a foothold or to do something more dangerous. So these are definitely things that I've recommended folks to go ahead and upgrade as soon as they can safely do so. And that's not just iOS things. Some of these CVEs are also in like WebKit and the OS on Mac OS and Apple TVs, watches, etc. So just upgrade all the things, particularly when you've heard that usually when a vendor like this says exploitation has been observed, it's a nation state or some kind of crime family. They're probably being very targeted towards their victims, but don't expect that to stay that way for very long. It's been weaponized, and because it's been weaponized, other people know it can be weaponized further.
Right. Quick question on the query itself, right? So here we're looking at the operating systems rather than product. Is that right?
Yeah, that's correct. In this case, it's just 2 particular operating systems, but those are easily adaptable to any of the others. In general, you can do a surprisingly good job at identifying operating system versions given the limited data that's available, and so you can help identify some of your assets that way. This is also another great way to identify assets that are EOL, because Apple iOS and iPad OS are there's often a ton of folks who don't upgrade. And so when you're looking to patch this particular vulnerability, you can also identify those people who don't even qualify for a patch because their OS is so old. It'll never be patched in those.
All right, let's go on to VMware, and this one's back to HD.
Sure. So a lot of folks, separately from the vulnerability, it's worth mentioning that so after the Broadcom purchase of VMware, they shut down a lot of the free products, like most of them. So vSphere Hypervisor. But I got a wonderful tip at the S4 conference last week, which is that if you join the VMware user group, vmug.com, you can get a $200 license to all the vSphere stuff for your home lab for non-production use. And that is not going away. And it's been confirmed by Broadcom that they're not getting rid of it. So if you're looking for a cheap lab license at this point, vmug, vmug A Advantage is the program there. And it's about $200 and it gets you all the VMware kit for your lab without having to deal with kind of the death of VMware Hypervisor free. But separate from that, so this set of vulnerabilities developed by VMware is related to the USB controller, the virtual USB controller, and the hypervisor itself. And the vulnerabilities allow you to break out of the OS into the hypervisor itself to leak memory from the hypervisor back in, and effectively get remote code execution on the base system, whether it's VMware Fusion, VMware Workstation, or the ESXi host. Kind of a funny aside here is forever ago, probably like 15 years ago, I was contracted by a firm to do fuzz testing, just to join everything together on the VMware IO port interface way back in the day. And I spent all this time going through and running fuzzers for it, doing IO port stuff, finding all kinds of fun bugs. I thought it was hotness. I thought I had all the cool stuff. I went to the CannSec West conference to meet the person who hired me to do this stuff, which is the consulting firm. And at the same conference, Tavis Ormandy got on stage and dumped every single bug I found, along with 300 more, all in a single presentation. And I felt like an absolute loser. So it was really cool seeing like these bugs pop back up again. It's like, oh, I remember looking at this stuff way back in the day, like trying to figure out how do you fuzz the USB controller of the driver and all kinds of stuff like that. So these bugs are important because they allow someone to break out from your guest VM into the rest of your infrastructure. This is important if you're running malicious payloads. For example, if you have a VMware box you detonate malware on or running a malware sandbox, these allow the malware to leave your sandbox and then take over your environment. So they're important. It's worth patching. And again, if you were running a license that is no longer available, the cheapest way to get that for your lab, at least, is the vmug membership.
All right, thank you. And we'll finish up with Rob on Open Edge.
Open Edge. Yep. So this is interesting. So Open Edge Progress, Open Edge stuff was they do what's called a 4th generation language. That's not all they do, but it's an application development platform thing. And there was as an aside, there was a these were very common in the 80s and 90s and all the way up to today, and I just love them. I have they're such neat systems. But anyway, so in particular, there was the Progress Open Edge, which lets you put authentication in front of your Progress application, and with authentication, you wanted to authenticate, and this allowed you to bypass that. So this was a pretty interesting and severe issue. They patched that pretty quickly, but it's worth noting that oftentimes these authentication gateways are placed in front of lots of different things. So if you bypass it, you get access to lots of different things. So worth noting, worth remembering.
All right, and just a reminder, everybody in the audience, with runZero, you can actually identify devices that are potentially vulnerable to all of these very quickly without having to rescan the network. This is why this research team does what it does to help everybody identify quickly these potential exposures that you might have on your network. All right, and that sums it up for episode 4 of runZero. I hope everybody registers for episode 5 next month. So this research team is actually producing a very large research report that's going to be published in May, but in the next episode in April, we're going to have a quick preview of what are some of the contents in that report. So I hope all of you will join us for episode 5 next month. Thank you, everybody.